All right, so we have come actually pretty far, and we have already seen the first law of thermodynamics. All right, and today we're going to deep dive into the material. I mean, of course, that means we're going to do some calculations here, and that's going to be a lot of fun. All right, so that means that you're going to have to bring everything that you have learned in the past 2 weeks and then put them all in here. All right, and toward later, I mean, after you have practiced all those stuff, then we're going to discuss even further how those first law of thermodynamics processes and all this stuff can be applied to a little bit more realistic applications. All right, sounds like a good plan. All right, I think you're gonna see something fun today. Okay, but first of all, let's recap a little bit quickly. So I just give you this slide right here just to remind you what we did last time. We know that we're going to use a lot of PV diagram. So it's a diagram that explains gas. And the reason that we use a lot of gas in our examples is because it's so easy to track, easy to see the change, and the property of the gas can be described using only single equation right here, the equation of state. All right, for the ideal gas, everything is good. So when we have the P, when we have the V, that means that once we get to the PV diagram, a point or a line in the PV diagram will let you know what is going on with the gas. Nice. All right. So we got that one. And then we know how to interpret a couple of things. First of all, the area under the curve. We know that if you have area under the curve, then you can calculate the amount of work that is being done. Okay, and if you know that it is an expansion, gas perform works itself. So the W will be positive. All right, that was the sign agreement. And if the gas contracted or shrinks down, that means somebody is perform some work on it. So the gas is being done on. The W will be negative. All right, sounds good. Okay, that's first thing. Second thing is we know from this that actually we have ability to calculate the total amount of kinetic energy in the gas system using this formula right here, 3/2 nRT. All right, for a monatomic ideal gas, you can use this equation to calculate the what we named internal energy, which is the average total kinetic energy of the system. That's a mouthful. All right, but now we can call this whole thing simply internal energy. And the nice thing about this one is it only depends on temperature. So that means every time that you have temperature change, you know right away that the energy of the gas has already changed. And that's why we face this special process right here is if the temperature is fixed. So what if the temperature does not change? You're going to get no change in internal energy. All right, we call this isothermal process. All right, cool, sounds good. All right, and we even added that if you keep the temperature fixed, what you get was just the P and the V must always be equal to a constant. And that means you're going to be able to trace a curve in the PV diagram that looks like that faint green line right here. We call this isotherm. Cool, so far so good. And this isotherm depends on the temperature. The higher the temperature, this line will lie higher and higher in the PV diagram. All right, so that's sort of like you can use this as a guideline to keep track of the temperature change. If the gas does not change in temperature, it must stay on one isotherm. It cannot jump out of it. It has to stick with it. So that's why the isothermal process is the process that actually riding along or riding on a single isotherm right there, not jumping out of it. Sounds good? All right, there's a question comes in. What's the distance between each isotherm? All right, so that's a good question. It depends on the temperature difference. Okay, so that means I can actually label this. For example, this is just no scaling or anything, but I can say like, hey, this is 100 Kelvin temperature is this line. This could be 200 Kelvin, 300 Kelvin. So that means the distance between the isotherms depends on the difference in temperature that you want to draw. Okay, so the bigger the difference, of course, the distance between isotherm will get larger and larger. I mean, but each single temperature will have its own isotherm. Okay, sounds cool. All right, and we ended up with the last process. We say, hey, what if we do not allow heat to exchange whatsoever? So maybe we put like an insulator on, or maybe some process is just changes so quickly or something like that. So if there is no heat exchanged, then you get adiabatic process. All right. And we discussed last time. Okay, let's remind you. First law of thermodynamics looks like change of the U equal to the heat flow, subtract out an amount of work done by the gas or by the system. When the Q is not allowed, so the Q is gone. So you can see that the change in the internal energy is going to be negative of the change of the work done by the system. And this is the reason why if the gas perform work, so that means if gas is expanding, W is positive. You guys with me? W is positive means gas is expanding. You're going to get the negative impact on the change of the delta U. With me one more time. When the gas is expanding, W is positive. When the W is positive, the net effect on the delta U will be negative because of that negative sign in the front of the W. And that means the delta U is negative. And that means the temperature also has to be negative. With me? And when the negative delta T happens, that means you are changing the temperature, but the change is in the downward direction. So that means in this adiabatic process, while the system is being expanded, W is positive, your temperature will be lowered. And that's why adiabatic curve, you're going to have a jump down from higher isotherm to a lower isotherm during the expansion. Cool. All right. Oh, I forgot my sound effect, right? I suppose you have somebody say, all right, or something like, okay. Oh, okay. All right. So I think that's good. Okay. Everyone is up to this point. So far, so good. I hope. All right.
Okay.
Okay. All right. If not, we'll see. All right. Let's jump right into the calculations. All right. We have some more detail, of course, that we have to go through. All right. So let's go through it. All right. So, I mean, you can flash through this one, the way that we calculate stuff, but we're going to sort of dig deeper into examples and how to utilize all the detailed calculation that we did last time. All right. We had done some calculus. We had some relationship that's going on in the adiabatic process. I think you guys like sort of like, all right, I sort of remember vaguely last week. All right. Let's take a look at one example right here. Let's start from an easy one first. All right. So today is going to be like a workshop, the first half of the lecture, because we have like a several examples that we can go through together. So I think it's going to be fun. That's what I say. All right. Figure shows a PV diagram for an ideal gas in which its absolute temperature at B, all right, right there. Just look at that point B right here. Yeah, there you go. Is 1/4 of its absolute temperature at A. So what I can say is, okay, T at B is T at A over 4. Does that make sense to you? First of all, just discuss this. All right. The reason I say that makes sense because once again, every time that I see PV diagram, usually in my sort of my brain or my imaginary visualization or whatever picture in my head, I can see that point B must be on one isotherm. Right? Every point on PV diagram must be on an isotherm because it must have some well-defined temperature. So it has to be on one. Oh, it doesn't look nice. Okay. All right, it's one of these, like that. Cool. And of course, A must be on one isotherm, but in this case, it's not going to be the same one. So A itself will be on another isotherm. Oh, that looks bad. All right. Okay, right there. Okay. All right, cool. And as you can see, we just discussed, the higher the temperature, the higher lying isotherm. Make sense? All right, so that's good. So temperature at B is supposed to be lower than the temperature at A. And the fine detail information they say is 1/4 of the temperature at A. So perfect. So this is good. All right, now questions. A, what volume does this gas occupy at point B? Can you figure out? You say about that, that's no big deal because we can actually read out the value on the diagram. Okay, so let's take a look at this. You know the volume at A is 0.5 liter. You even know the pressure at both A and B because this one is isobaric process. You can see it's just an horizontal line. So the pressure does not change. Cool. How can you figure out the volume at point B? As you can see, this is not thermodynamics just yet. This is just a question about the gas, it's gas itself. So let's do it. PV equal to nRT. And we also have P1 V1 over T1 equal to P2 V2 over T2. Yeah, okay.
Okay.
Cool. All right, so with that, that means you can compare these 2 points, A and B, using just this relationship right here. Okay, and even better, pressure is exactly the same. So I'm gonna write it down like this. Part A, it looks like PAVA over TA equal to PBVB over TB. Pressure cancels because they are at the same temperature. So from here, you can see that the ratio between the volume and the temperature is going to go together hand in hand. Because the temperature at B is 1/4 of that at A. So you probably can say, okay, the volume is going to be 1/4 of the volume at A as well. Done. That's it. Right there. So it's going to be 0.125. Cool, guys? Yeah. So I hope you start to see how to actually do the calculation. Yeah, very good. PV equal to nRT. Let's do that. All right. Part A is no problem. Part B, how many joules of work was done by or on? All right. So this one, that means the question asks you to determine the sign of the W on the gas in this process. Was it done by, okay, this is typo right here. Sorry. I think that's get asked twice. All right. Okay. Let's calculate the work done, shall we? All right. Part B. So the work done, all right, let's start from the pure, like, down to the definition of this one is the integral of the PDV. Cool. But of course, in this case, pressure is constant. So I can pull P out from the integral from volume at A to volume at B. So far, so good. All right. And you get P times V, and then you put the lower limits and upper limits right here. I'm just trying to go through like a calculus-ish method. All right. But at the end, you guys know it's going to be P delta V. It's just area under the curve. But the good thing about doing this whole thing in like a correct mathematical procedure right here is because the sign will pop up at the end automatically. Can you see this? Because once I substitute the upper limit in here, it's going to be V at B. When I substitute the lower limit in there, it's going to be V at A. And you guys can see that from A to B, the volume of the gas is smaller. So that means the final numbers that you're going to get is going to be automatically negative. Nice. All right. So if you want a number, you can plug it in. Let's not do the unit conversion right now. All right, running out of space right here. All right, so it's 1.5 ATM for now. All right. And I can do the volume change right here. Volume at B is 0.5. Volume at A is 0.125 liter. Already. All right. At the end, it's going to be negative number. All right. So I leave you guys to do the actual unit conversion and all the detail like number crunching and all the stuff. But at the end, the W must be negative because we know gas is contracting. So definitely work was done on. Of course, it has to be. Okay, because if work was done by the gas has to expand. But this one, the gas is being done on. Okay, something is just compressing it down. You swap the number. Sorry. Thank you. My bad. My bad. Oh, just yeah. Over advertise. Yeah. Sorry. 0.125 minus 0.5 liter. Okay. Thank you so much. All right. Got it. I just want to check that you guys are like sort of paying attention or not. Yeah, you know. All right. Okay. Part C. Oh, do I have enough space here? Okay. That's gonna be a lot of. I should have. Now I need more space, but I didn't prepare for that. In the previous slide, I had some space I didn't use. All right. But maybe you can just answer part C right away. Did the internal energy of the gas increase or decrease? All right. We don't need calculation. It's just asking. What happened, guys? Part C. What do you think? The sound doesn't come out. Decreased with a question mark. That's nice. Very good. That is correct. All right. The reason is because, of course, it's jumping down. You coming from A down to B. You starting from higher isotherm down to a lower lying isotherm. So that means you know right away. I can put like a quick highlight here. This is going to be temperature that is high. This is going to be low. I mean, no, I don't know how low, but actually it's low. So definitely in this case, the internal energy has to be lower as well. Perfect. Very good. So part C, delta U is negative. So that means U decreases. Oh, shoot. Okay. Delta T is negative. So as delta U is negative, so U decreases. Okay, here we go. All right, that's part C right there. Okay, very good. Oh, I think I did something wrong here. Sorry, I just switched my speaker microphone. Oh, are you guys, the sound is good? Okay. Oh, I did something to my setting. Sorry. All right, just let me know if there is any problem with the sound. Speaker, USB, all right. Better. Oh, shoot. Sorry, guys. So it must be microphone from the notebook. Shoot. All right, so I hope this one comes right from my microphone now.
Okay.
Okay, let's check a little bit. Shoot. All right, so I hope it's better. It's changed for like only a few minutes. Oh, okay, so it's fine. Okay, thank you so much. All right, guys, let's get going.
Okay.
All right. Part D, did heat. Now, we talk about heat, so it must be related to the first law of thermodynamics for sure. The question is, does heat enter or leave the gas from A to B? So good thing is, for this exercise right here, part C and part D is still sort of like qualitative questions, right? You don't need to calculate just yet. All right, but what happened to heat, guys? So this one is gonna get more complicated a little bit, but that's how you practice using the first law of thermodynamics. Heat enter or leave the gas. Leave. All right. Leaves. Okay, very good. Very good. Looks good. Looks good. And I hope you guys knows how to determine this systematically. All right. So once again, all right, for those of you that are still sort of maybe confusing a little bit, don't forget we have only one single relationship here. It's first law of thermodynamics. So delta U equal to Q minus W, correct? Okay. So now we are focusing on the Q. So Q is delta U plus W. We practiced this already last time. Oh, okay. All right, very good. So with that, Delta U, we already saw that is negative right here. W, we already saw that is also negative right there. So it's guaranteed that the Q has to be negative overall once you're done with that summation right there. So net Q you're going to get is going to be negative something. Yes, and the answer is heat will leave the system. All right, and the internal energy decreases. All right. So get the feeling of what is going on here. All right, so it seems like at the end, you're going to apply either equation of states because we are looking at the ideal gas mainly. And in the case that you are interested in the internal energy, the work, or the heat, then you have to use first law of thermodynamics. Sounds good? All right, try again. Here we go. Okay, you guys try this. All right. I'll give you like a couple of minutes head start right here. All right, but let's read the question through together for the first part of this problem. You have an ideal gas taken from A to B using that PV diagram below. Okay, during this process, now information is you have 700 joules of heat added. And another information here is the pressure is double. So actually, I can actually draw this one right here. It's 60 kilopascal on the PV diagram. A, how much work is done? How much work is done? Very good. Okay. Thank you for the answer. All right. If no answer, then that will be bad. All right. The reason is 0 because there's no area under the curve. The volume does not change. Gas does not either expand or contract. Nothing is going on. So part A is good. 0. Simple. B, how does temperature of the gas at A compare to the temperature at B? All right, you guys go ahead. How to attack this one? All right, I'll put some charger on. Okay, give me a second. All right, just work on this. All right, it only takes, I think, 1 or 2 minutes. Oh, okay, it's back. It's my switch. No, it's me. It's me. I just hit the switch on my microphone right here. Sorry. Okay. All right. So part B. Okay. What about the temperature? Once again, it's asking just about the property or the states of the gas. So you still don't need to use first law of thermodynamics on anything just yet for part B. For part B, once again, you do PAVA over TA equal to PBVB over TB. Okay?
Okay.
All right, very good. T at B is going to be higher than T at A. Definitely for sure. Once again, if you like my idea of overlaying some isotherm on top of every point on the PV diagram, P is going to lie higher in on the isotherm that lie higher than point A. And because this particular one, you see that, yeah, it's a constant volume process. V automatically cancels. Because you know that the pressure is double, so the temperature will be double too. So at least you know that the T at B will be twice the temperature at A. Cool. All right. All right. Oh, and the U at B, yeah, definitely. So once the temperature is higher, the internal energy will automatically higher as well. Correct. And another comment, and T at B is 701. How do you get 701? 701. What this number is from? Not so sure. I cannot see these numbers just yet. Up to this point, what I can say is, up to this point, it's just twice the temperature at A. But okay, about to, let's move on to part C first, shall we? Because part B is just asking like how does the temperature at A compare to at B? You just say, okay, it's twice as big. Okay, all right. So there is a question comes in. Okay. This is a very good question. I will answer that later, right, in a little bit. All right, give me 1 second here. All right, so now let's answer part C. What do you think, guys? Part C. How does the internal energy of gas at A compare to the internal energy at B? Well, Ajahn, of course, the temperature is twice as big. Okay, so if you refer back to the expression for the internal energy, U is depending on T as well. So that means U at B will also be twice of the U at A. Okay, looks good. But then if you remember, all right, go back a little bit, back here. We already discussed in detail on this kind of process, right? It's an isochoric or constant volume process. So over here, if you really want to draw or sort of write the whole expression for the change of the internal energy. Okay, let's me redo everything one more time. So what I'm trying to do is I want to go systematic. I want to start from first law of thermodynamics all the time. So from the first law of thermodynamics, change of the internal energy is heat minus work. Cool. This one, there's no work because volume does not change. So the amount of heat will be automatically related to the change in the internal energy. But then everyone knows that the U of an ideal gas, monatomic gas, is 3/2 nRT. So that means over here is going to be 3/2 nR delta T. Okay, cool. All right. And what you can get from here is, last time, we can rewrite this one a little bit, make it look like MC delta T. But it's not the M anymore that we are interested in. We are interested in the number of mole, the N. So it's going to be N times the specific heat per mole. You think of it like instead of per kilogram, now it is per mole. But we still name it specific heat anyway, if you like. So this is a specific molar. It's a molar is per mole. Molar specific heat in the constant volume process. And then you calculate. And then you multiply by the delta T. All right. So I hope this remind you things that you have done, we have done in the past. All right. Good. Okay. So what is, well, we can actually do further, but because this problem doesn't really ask you to do it, but if you really want, we can do it right here. Okay, follow me a little bit here, guys. Look at this one is 3/2 nR delta T, right? So if I write this one down as 3/2 nR T at B minus T at A. You guys with me so far? All right. And that means I can keep going is 3/2. And you look at this nRT is just PV. So it's going to be P at B, V at B minus P at A, V at A. Still with me? Because PV equal to nRT all the time. And if you look at this, P at B, V at B, P at A, V at A, you can read out from this PV diagram. You know exactly what's supposed to be. Let me keep going. 3/2, actually V is the same because volume does not change. So I can do P at B is 60 kilo minus P at A is 30 kilo. Let me just squeeze in the K for now. Times the volume 0.05. Okay. So with this, you're supposed to get back the Q right here if you want to. So is that 700? Is it supposed to be 700? Yeah, 39, 945. And that looks really bad. 455. Yeah, that looks pretty bad. In somehow jingle bell note in your PBVB minus PAV. What is that? Jingle bell note. Okay, anyway. All right. So this is a problem, guys. I think I saw a problem. It's maybe my typo or whatever. All right. So this is the case that it's actually part of it is my mistake right here. I don't know if once I plug in everything here and calculate everything, will I get 700 joule back or not? All right. So this could be my bad. And this is something that we say is overstated information that inconsistent. All right. So this could be my bad. The reason is actually you should be able to calculate this number yourself, not from my question, right? I don't know why. I think I messed up something here. All right. But actually, if you don't know this 700 joule, okay, if you don't know, you should be able to calculate the amount of heat flow using that bottom down in the bottom right corner calculation right there. And that will allow you to calculate the Q using the value from the PV diagram. Okay, you guys with me? Thank you for that. Okay, somebody worked out the number for me. It's 30,000, thank you, times 0.05 times 3. All right, it's 2250. That's supposed to be the heat during this process, guys. Thank you. But I hope you see, learn from my mistake right here. The information over there is incorrect. Because if you stick with the PV diagram, which is in this case, I mean, it's already give you everything pretty much, you will be able to calculate the heat from the PV diagram. Yes, not, yeah, 700. I think there was some added stuff that's not supposed to be added lightly. Yeah, it's supposed to be calculated, not supposed to be just added. But the things that we learn from these problems, and it happens to me many, many times. This is the I would say the cool, I don't know, it's called the cool thing about thermodynamics or anything. This is like you're learning like accounting. So that's why in accounting, you cannot just coming up with just like weird numbers, or you can just add some numbers, subtract out number without any documentations or any reference to anything at all. That's not right. Okay, so that's why I'm saying that learning thermodynamics is like doing accounting, or you can do like a, I don't know, balancing the statement or something. So it's just doing transactions in physics right there. Okay. All right. So sorry about that, but I hope these confusions allow you to clear things up about when you really read something out from the PV diagram, and then use those information from the PV diagram to calculate things using first law of thermodynamics. If the information is already complete or enough for you to do calculations, the equation that you use will pop up the final answer, all right? And if you want to assume some other numbers, it's going to be inconsistent, like I did in this example right here. Sorry, that, I don't know, it's kind of bad examples, but yeah, I didn't change this slide in time, so it's already there. So I had to talk about this like upfront right here. Okay, I hope you guys with me so far. All right, now there was a question talking about this. There is a question. Let me go back a little bit. So now, if I have a statement saying that if the pressure increase leads to temperature increase, yes or no? Okay, come again. If, okay, let's say I have a gas in this room. Somehow, if I increase the pressure of the gas in my room, that leads to the higher in temperature, yes or no? Okay, let's say I am part of the molecules in this big room, think of this room as a container, and then somehow the pressure rises. So I have higher temperature. Pressure is increased by somehow somebody may be pressing down, or I don't know. There's no information there. The only statement saying that when the pressure in this room is higher, that means the gas in this room have a higher in temperature as well. Yes or no? Yes. Okay, that's some yes. That's some no, not necessary. Okay, very good. All right. What do you think? Higher pressure mean higher temperature. What do you think? What do you think? Some more participants, right? All right. The answer now is, I think that's one correct, not necessary. Okay, I'll give you a second statement. If I give this room some heat, the gas in this room supposed to be higher, yes or no? Well, maybe this one is not so clear, but I mean, you can imagine on yourself. If I have a container, I provide some heat to the gas in the container. I say the gas in that container is supposed to get hotter, higher in temperature. Yes or no? All right, it looks like yes. Yeah, it sounds common, right? Okay, so here comes the key conclusions, and that's the part that I really want to stress. You need to know everything before you answer the question, because what we are learning right now is the first law of thermodynamics, guys, right there. Yeah. So now the player that comes into play is heat, and you have work, and of course this is temperature change. So from now on, when they say, hey, if I give a gas some heat, the gas will get higher in temperature, yes or no? You have to ask me back right away. Does the gas expand? You guys with me now? Because just those statements, what I'm saying is, I'm talking about, I'm providing some heat. I want to know what is going on with the temperature change, but I still don't know what is going on with the behavior of the gas with respect to the work done. With me now? Same thing. Okay. If I'm just saying that, hey, the pressure of this gas in this room is just higher, I cannot say much about anything, because what I know is just, okay, the pressure of the gas is higher. All right. There's no doubt about it. But then I'm still missing about what about the volume change, or what about the heat? Is there any heat flowing in or out? So that's why this is tougher to answer now once you study thermodynamics, because there are three parties that is playing at the same time. Okay, but common sense, of course, you will say, hey, Ajahn, I'm heating up some gas, the gas is supposed to get hotter in temperature. Because in general, when you do something like that, the amount of work done by the gas is pretty much small. Or maybe you put a gas in a tank. When you put a gas in a tank, then you automatically assume that there's no work done. So that's, of course, that's easy. When there's no work done, you give some heat, of course, the temperature will rise, because these two things will happen in the same direction. So that's good. All right. But in the most general setup, if I warm up some gas, but it might be a case that gas itself is also expanding. And it's possible that the expansion of the gas, the W, is expands so fast that the work done by the gas is actually greater than the amount of heat that I provide to the system, to the gas. So net result, you might get the negative number at the end. So there is a case that actually when I provide some heat to the gas, but the gas is expanding, the temperature can be lowered. You guys with me now? I think that's the thing that's sort of counterintuitive, because back in the day of Newtonian physics, you do not think of this yet, right? In Newtonian physics, you purely talk about work. What is work? You're doing mechanical work. All right. But then in simple heat, like you can think of it like calorimetric calculations, you still don't talk about W. You do like Q equal to MC delta T, Q to MC delta T. You assumed that heat will translate into change in the temperature right away. But now once we at a point that we can combine them all, then you need a full information to be able to answer all of the stuff here. Okay, that's that sort of maybe sound tedious. I'm going back and forth, but I hope that'll give you an overall sort of like interrelationship between these three terms, and that allow you to be more cautious about answering some question. And turns out most of the answer turns out to be like not necessary, because there is some possibility that you can adjust on the third parameter, something like that. Okay, guys, I hope that's not confuse you in any way. All right, I hope. All right, let's do one more. All right, or actually one or two or two more. Oh, actually I have three more. All right, anyway, we'll just keep going. All right, today is like a workshop. You need to understand this, because once you understand this, the application will be, I would say, very straightforward. Well, I wouldn't say easy. I was about to say easy, but well, it might not be easy, but at least it will be a very straightforward extension to what you have done here. All right, so let's complete this whole thing. All right, PV diagram shows a series of thermodynamics processes. In a process AB, all right, AB, 150 joule of heat is added to the system. BD, 600 joule. All right, just to be able to put the heat in the PV diagram, what people usually do is they just put an arrow into it. 510 joule. All right. And when you say added, that means I put an arrow toward the right side because of something that I'm going to explain a little bit later. All right. And BD, heat is added. When I add it, I try to put it down here. Okay. And then find the internal energy change during the process AB. Let's start from part A first, guys. They want to know the heat, I'm sorry, the internal energy change from A to B. All right, go for it. Let's give it a shot. I want answer from you.
Okay.
Seriously. Part A. Go from A to B. There is a heat added to the system, 150 joule. All right, information on the PV diagram is obvious. You can read from the scale. What is the internal energy change from A to B? All right, so that's one answer submitted here. 3/2 times 5 times 10 to the 4th times 2, 10 to the negative 3. All right, that looks pretty good. And that's 150. All right, nice. I'm not so sure about the first line, but 150 is good. 150 is good. All right. For those of you that's still thinking, don't think too much. Whenever we talk about internal energy, heat, work, or the stuff, that means you need first law of thermodynamics, right? So what you can say is, all right, change of the U from A to B is going to be equal to the heat during AB process, subtract out the work done during AB process. Now, let me put just AB, mean A to B. Okay, cool. But you can see from A to B is a constant volume process. This one is gone. But then the problem already gave you that during this process, there's 150 joule added to the system. Added to the system means positive heat. That's it. It's done. So the internal energy change from A to B is supposed to be 150 as well. But then this is a good example. The reason that I say this is a good example without inconsistent numbers is because if you read the volume, the pressure change, and you put this into 3/2 nR delta T, which is going to be 3/2. Okay, you guys with me? P at B, V at B minus P at A, V at A. This is going to be exactly your friend just gave us those products between a couple numbers. It's going to be 3/2 pressure at B, 8. Okay, actually I can pull out the volume because the volume is the same. So it's 2 times 10 to the negative 3 cubic meter. That's for the volume, both V at A and V at B. I pulled it out to the front. And then I multiply by the change in the pressure between B and A. And that's only 5 times 10 to the 4th Pascal. And that's the number that your friend just gave. And for the good problems like this, these numbers end up the same as 150. So this is a good one. Not my previous one, which inconsistent between the PV diagram and the given numbers in the question. All right, guys, sort of pretty good. Get a sense of what is going on with the first law of thermodynamics. All right, try again, part B, guys. Internal energy change now from A to B to D. They want A to B to D. All right, the good thing about this one is, all right, remember we talked about the convenience of having energy. When it's energy, you only care about positions. You don't care about path, pretty much. So going from A to B, D, to B, and then to D like this. Okay, delta U going from A to B to D is pretty much is going to be exactly the same as you can go from A to B first, and then you follow by B to D. That will work too. It doesn't really matter how, right? As long as you end up at point D, everything is good. Okay, all right. So that's give you a sort of like a clue already that, hey, Ajahn, I already got this part. This part is good. All right, because we got that one from the first half of this one. All right, so this is fine. So the only thing left for you to calculate is what about the total energy, I'm sorry, the internal energy change from B to D. If you can figure out that, then you just add it with the 150 that you have already found out. That will be your net change from A to B, then to D. All right, guys. Find me the change in the internal energy from B to D.ค่อยๆทำ Just make sure that you know how to do this, right? Just like, you know. I want total internal energy changed from B to D. All right, it's kind of quiet at this point. I hope you guys sort of like, you know, doing heavy calculation at this point. oh, that's submission there. Okay, B to D is 360. Okay, very good, very good, very good. What about the one on top? That's a lot of numbers right there. Whoa, I have to calculate first. What's that? Okay, can you give me? All right, okay, very good. All right, seems very consistent. All right, nice. What about the rest, guys? Get same sort of like the numbers right here, but you got in the right direction here. You need to figure out the work. Okay, so let me explain this portion. Just for this portion right here, you need first law of thermodynamics again. So just to get to this, it's going to be equal to the heat from B to D plus, subtract out the work done from B to D. You guys with me now? That's pure first law of thermodynamics again. But then the problem already give you the heat during B to D process to be 600 joule. So actually this waiting for you already right here is 600 joule. That's good. The only thing that's missing here is just this portion right there. The work done from B to D, but that's not hard because this B to D process is a constant pressure process, isobar. So area under the curve looks like just a rectangle. That's nice. That's a W from B to D. You guys with me now? All right. And that means you will be able to calculate this rectangular area right away. It's going to be 8 times 10 to the 4th. That's the height times the width right here, which from 2 to 5, the change is 3. So it's going to be 3 times 10 to the negative 3 cubic meter. And that is the amount of work done from B to D. And as you can see, we know it's supposed to be positive because gas is expanding. All right, I'll just keep going. So it's going to be 600. Subtract out that 240. All right, just this part alone give you 360 joule. So very good, guys. All right. Big hands. All right, next. Everyone is happy because it's not a curve. All right, guys, you guys sort of influence in calculus, right? You guys can speak calculus language, so you should be fine, even though it's a curve. All right, so once we get this number 360, then, all right, we know the first one is 150 from part A, and that's it. At the end is 150 plus 360, and that 510 joules. All right, so I hope you sort of see how things goes with the first law of thermodynamics. And part C, what about the total heat? Okay, let's do part C and then we take a break. Sounds good? All right, so part C, the total heat added in process A to C to D. All right, this is a little bit more challenging, I think. I speak alpha Wolfram language. All right, that's fine. For this millennium right here, we can forget about Newton and calculus. All right, let's speak like Wolfram alpha. That's nice. I think the only people laughing something like this is just us, right? We are like geeks, nerds here. All right, guys, part C. Find me the total heat added in the process. Now A to C to D now. They don't want to follow the same path. They want to go from A now to C up to D right there. All right. You might find this a little bit harder than the previous one because it's sort of like a total heat. No heat add. Okay, that's one submitted answer right here. No heat added during A to C and C to D. Cannot tell. Not, no, I don't know. But I think there must be some. From the look of it, there must be some. All right. What do you think? Delta U is path independent, so it's 510 joules. That's good start. Perfect. That is very good. One thing to keep in mind that it doesn't really matter how you get from A to D. As long as you get from A to D, the delta U from A to D still 510. That's nice. All right, that's already 50% done right there. So this path right here, the delta U from A to C to D, still same value, 510 joules that we already calculated. So what's missing, guys? Almost done, almost done. All right, once again, you apply first law of thermodynamics. They're supposed to be equal to the heat from A to C to D. Subtract out the work from A to C to D done by the gas. Yes? All right, so this is the one you want. This is the answer you like. So the only thing left for you to calculate is this dude right here. If you can figure out the work done from A to C to D, then you move from the right side of the equation, add it to 510. You get the heat during the A to C to D process. Sounds good? All right. Now Question is, what is the amount of work done from A to C to D? Everyone just like, Ajahn, happy. It's just area under the curve. So it's going to be just that rectangular area underneath. The one that I highlighting, that red shaded area right there. Okay. And, well, Ajahn, I can go for it. That is W A C D is just this width times height right there. And that 90, just like your friend just gave me. Very good. Right? And that's it. So I know this one to be 90 joule. So the answer, oh, my slide looks very dirty, but I hope you still follow. That is 600 joule. There you go. I just moved 90 to the left-hand side, add it to 510, you get 600 joule. And that is done. Cool. As you can see, the amount of heat is different from A to B to D, because from A to B to D, you see that the total heat that flowing into the system is total of 750. But going from A to C instead, then get to D, the heat takes only 600 joule. It takes less heat. All right. But the thing is, it takes less heat, but gas perform less work as well. Okay. So that's why it has to go together, because the change in the internal energy are the same in both cases. Yeah. Delta U has to be the same because you start at the A, you end at D. So delta U must be the same on both. So you can expect that when you go from A to C to D, the area under the curve is smaller. The area is smaller. So the heat is supposed to be smaller too, because you don't need a lot of heat, because you don't want to perform a lot of work. Something like that. Sounds good?
Okay.
All right. So if this is good, then I think this is a good point to take a break. I will come back and finish up the rest of the problems. Sounds good, eh? So how do you like this? All right, next example. The graph in the figure shows a PV diagram, of course, right? But now we know it's a 1 mole of gas. Now part C and D, it says it's isothermal. That's good. Okay. Part A, find the pressure of this, or is helium, all right, at point A. All right. Of course, we treat helium to be ideal gas. We don't know how to treat things other than ideal anyway. So, all right. You guys, part A. Go for it, guys. Part A. Now, once again, part A is asking about the state of the gas. So you don't need to think of the thermodynamics just yet. It's just asking for the pressure at point A. So once again, you want to compare point A to other points. So you recall PA over TA equal to, and then you can pick any points you like. You can pick a point P or you can pick point C, but from the look of it, point C seems to be a very complete point that allow you to know both pressure and volume really well. So I'm just going to pick that point. Why not? All right. And the good thing about this one is point A and point C supposed to be on the same temperature. You guys with me? Yes. Yes. So that means these two temperatures are exactly the same. Or speak in another terms, these 2 points lie on a single isotherm. With me now? Because they say CA is isothermal process. Cool. All right. So with that, things turns quite easy now, I guess, because PV equal to constant. Yes. All right. Give me the answer, guys. Oh, I forgot to turn on my. All right. I'm here. Okay. All right. PV equal to constant. So that's it's done, because you can see that at point A is 1/4 of the volume at point C. So of course, at point A, the pressure is supposed to compensate to be 4 times higher in pressure than point C as well. You guys with me, yeah? So from this, that leads to P at A to be 8 times 10 to the 5th Pascal. All right, or I can just draw it on here. It's supposed to be 8. Okay, good. Okay. Next, part B. Find the temperature of all points, A, B, and C. How are you going to do that? Once again, it's still asking about the state of the gas at this point. So you probably will be able to get away with just equation of state somehow. Okay, part B. Okay. Anything? All right. So from the look of it, Ajahn, this is not bad because if you look at point A, you know both P and V, and of course point C will do the same thing. So from that, actually, is one mole of ideal gas. So PV equal to nRT. You can pick a point, for example, point A. So it's PAVA equal to nRT at A. P is known, V is known, N is known. You can figure out the temperature at A right away. Like that. All right. So T at A is supposed to be P at A VA over NR. And that's it. T at A is going to be, now I can plug in the number. P at A is 8 times 10 to the 5th Pascal. Volume at A is 0.01 cubic meter. Over N is 1. R, just leave it as R. I don't want to mess up with the number calculation or anything. It's just because it's a constant, so just leave it as R. So over here, I'm having what? 8,000 over R. That's my temperature at A. You guys with me? Okay.
Okay.
And then this is going to be temperature at C automatically because they both are at the same temperature.
Okay.
The only thing left for you to calculate is the temperature at point B. But that's not hard because at point B, once again, you can link point B to A or C using PVVB over TB equal to PAVA over TA. I don't know, it's like something boring like this. It happens in maybe back in the chemistry day or something. I'm blaming chemistry here. All right, but anyway, it's just comparing, or you can compare to the point C if you like. But the good thing about either A or C is, I mean, there will be some parameters get constant value, so they can be canceled. Like for example, in my case, I'm comparing between point A and point B. Pressure are exactly the same. So this one is, I mean, this PB and PA cancel out. And then you just compare the ratio between the volume and temperature. Okay. All right. And once again, from A to B, the volume is 4 times bigger. Of course, the temperature has to be 4 times larger as well. So what I can get from here is the temperature at B is going to be 4 times the temperature at A, according to the ratio of the volume. And that's it. So temperature at B is going to be 32,000 over R. All right. In the exam, I think I don't mind if you want to leave R alone like this. I think to me, it seems even cleaner than you just plug in the R and punch the calculator. Okay, sounds good. So I think just leave it as R is nice because you will see it in a little bit. Eventually it will get canceled with whatever other expression or equation that you use that has R on it. Then R in that equation will cancel with R in this temperature, and then it's good. It's just R just disappear from the equation. All right, but it's up to you. It's your preference. If you want to plug in the value of the R and then do the full calculations, get the final numbers. Or if you don't like, I think leave R as is like this. I think it's not bad. Okay, so you get temperature at all 3 points. So you're good. Part B is done. Any questions so far? So far, so good. All right, now part C, guys. How much heat entered or left the gas during each segment? All right, so this is going to be a little bit more challenging because this is like you're going to have to do them all. But let's start from each segment, shall we? Let's start from A to B, guys. From A to B. All right, let's remind you what this is. It's a constant pressure process. Okay, everything starts from the first law of thermodynamics, of course. But then you want the heat. And then you just said, Ajahn, this is constant pressure process. We did this before. I'll do it one more time. I'll do it a million times more. This is 3/2 nR delta T for sure. The work is going to be P delta V. It's a constant pressure process. But then I can turn P delta V into nR delta T as well. So this is nR delta T. So at the end, you can expect that I'm going to get that 5/2 nR delta T at the end. Why? Because this is a constant pressure process. You guys remember this one right away. So that means if you can match the process with the one that you have already know its characteristic, actually I can jump right into the final expression, say about Ajahn, is the constant pressure process. The heat in this process is going to be 5/2 nR delta T right away. So you guys with me now? So even though you don't know or you don't want to memorize this formula, you can start right from the first law of thermodynamics, get 3/2 nR delta T from the delta U, P delta V from the definition of work. You're going to end up with the 5/2 nR delta T without any difficulties anyway. Okay, sounds good? All right, with that, I'm done. I say heat from A to B is 5/2. N is 1 mole. R is R. Delta T is T final minus T initial. So it's going to be T at B minus T at A. But we have already known all of the temperature at B and at A. All you need to do is just substitute the value into it. T at B is 32,000 over R. T at A is 8,000 over R. See, good thing is R get canceled. Nice. So you get the amount of heat flow during A to B segments to be, what's that? 2412. Okay, 60,000 joule. Okay, let me write on the left here. 60,000. So it's 60 kilojoule right there. And it's positive. So what does it mean? It means the heat enter. Let me put enter. I'll put it down right here. Heat enter during AB segments to be 30 kilojoule. My number is correct. I hope I do my math right. All right. It's 24,000 divided by 2, 12,000 times 5, 60,000. Of course, it's a 60 kilojoule right there. And it's enter because it's positive. So I can emphasize that by putting the positive sign in the front. You guys with me now? Sort of get an idea? Okay. If this is good, you guys try B to C. Come on. B to C. All right. I think I can move on to the next page. I have some extra space right here. B to C. All right. So Q from B to C. If you want to jump right into the final answer, the reason is because B to C, the work done is 0. There's no work done. So that means it's going to be exactly the change of the delta U from B to C. And that is going to be 3/2 nR delta T. Yeah, constant pressure 5/2, constant volume 3/2, and that's it. So it's going to be 3/2. N is 1, R is R. Delta T is going to be T final minus T initial. So it's going to be T at C minus T at B. And that is going to be 3/2 R times temperature at C is 8,000 over R. Temperature at B is 32,000 over R. And the nice thing about this one is, once again, R cancel. And as you can see, sign is automatic. All right, 8,000 and 32,000, you get negative 24,000 divided by 2. Okay, so it's going to be 36 kilojoule negative. Isn't that cool? Yes, yes, not bad, not bad. So that means going from B to C, heat leave the system. Or I mean, what you can draw on here is, here, I put the arrow out. When I say out, I'll explain more later. But it's 36 kilojoule out. And you just saw from the previous calculation that is in of 60 kilojoule right there. So get the feeling of what is going on now. All right, last portion. What about C back to A, guys? C back to A. Heat C back to A. But this one is good because it's an isothermal process. A and B has fixed temperature. Delta U is gone. Okay, so that means from the first law of thermodynamics, heat from C to A is going to be the same as the work done from C to A. But the work done, this is the one that you loved last time. We did some calculus here. It's just the area under the curve. Okay, and if you don't want to redo the calculation again, then you can just flash back and look at the result that you saw last time. Here is an nRT log V final over V initial. Cool. All right, we don't want to redo your calculation again, so that's fine. Let's use that result here is nRT, and then when you say nRT, it could be any T, T at A, T at C, or anywhere in between, doesn't matter, plug in there. And then log V final over V initial right there. Okay, all right. Substitute the numbers, N is good, 1, R is R, T at A is 8,000 over R, log of V final over V initial. You just need a ratio. You don't need actual numbers actually. So only things that you need is A is 1/4 of the volume at C. So it's log of 1/4. And once again is log of the number that is less than 1. You're going to get a negative result. R cancel. That's it. So it's negative 8,000. Okay, let me put in kilojoule. So it's going to be 8 log 4 kilojoule. Isn't that cool? All right, what does it mean by negative sign? It means that during this process, heat left the system. All right, color is not so contrast right here. Okay, let me put here. There you go. That's negative 8 log 4 kilojoule. And that's complete the whole process. So you start seeing now that, hey, we will have a chance to do all this stuff more and more, but that's pretty much everything that you need to know. Because in the first law of thermodynamics, you only have 3 terms. It's either U change, is either the heat, or is either the work. And they are all linked through the first law of thermodynamics. If you know how to calculate down to the heat, that means you have already learned how to calculate work and internal energy change. So you are in a good shape now, I think. Yes? I hope.
Okay.
All right, any questions up to this point? So far, so good? All right, so if this is good, now let's answer part D. by how much did the internal energy of the gas change from A to B, from B to C, and from C to A? But oh, Ajahn, this is like backward question because we have already calculated everything. So it's supposed to be simple. All right. So let's try it. Part D. Delta U from A to B, guys, is going to be what? It's going to be 3/2 NR T at B minus T at A. You guys with me? We already calculated this actually. All right. It's right down here. But anyway, I think actually I mean, look back at this. I should ask this question first. This is supposed to be like part C, and then heat supposed to be the part D, because it seems like we start to see that heat seems to be the hardest to answer, right? Other parameter in the first law of thermodynamics seems to have some formula or something that you can link to, but the heat seems to rely on the other two. But anyway, all right, that's not too bad here. So what we can get from here is just substitute in the number. N is 1, R is there, temperature at B is, all right, I should just actually move down here. Sorry. Okay. All right, there you go. And that will give me 32,000 over R minus 8,000 over R. All right, that's not bad. And then you keep going through the change of the U from B to C and C back to A. Okay, I think I should complete this one just to make it clean. Cancel. So this will give me 36 kilojoule right there. Okay. All right, and delta U from B to C is going to be 3/2 NR T final, T at C, minus T initial, T at B. All right. And it seems like is going backward. So I don't even have to calculate this one because it's going to be negative 36 kilojoule. You guys with me now? Yeah, because going from A to B, whatever the change is happening, you step right back in the same temperature as the A. So whatever you change during A to B, you change it back. So it's going to be negative of whatever the first part that you just calculated. Okay, that's a question comes in. Does UAB equal to QAB minus WAB work as well? Yes, it does. Yes. Yes. And if you try to do that calculation, you get the same answer. Yes. Oh, does it get the different value? No, it shouldn't be. The reason is not because when we were trying to calculate the heat, we sort of going through the delta U already. Let me see. Yeah, let me double check for you, but it's supposed to be the same. QA to B is 60 kilojoule, and the area under the curve, okay, right here, there you go, is going to be height. Okay, WAB is 8 times 10 to the 5th and 0.03 cubic meter. And that is 24,000. Let's put it in kilojoule. There you go. Okay. So the work done from A to B using the area under the curve is 24 kilojoule. The heat that we calculated is 60 kilojoule. So you take 60, subtract out 24, you get back 36. And it's right here. Oh, okay. All right, cool. But that's a good question, actually. This is something that you can go back and sort of like go forward, go backward, go back and forth, things like that to double check that to arrive at the final answer. It's just maybe I wouldn't say same equation, but it's like there are a couple of approaches that you can get to the final answer because they are all related, okay, among those values. And eventually they must be consistent with each other. It has to be. Okay, good. That's great. And the easiest of all is the delta U from C back to A. That's easiest because from C to A is on an isotherm. So C to A is an isothermal process. So the temperature does not change and the delta U is 0 right away. All right, is it good? All right, so if this is good, I think I'm not gonna try to push too hard. I think I'm gonna, in terms of the practice exercises and showcasing how to do detailed calculation, I think you have enough to see today. What I would like to close today's lecture is what this whole thing or what this whole calculations can lead you to. All right, and that will be the opening for the rest of the thermodynamics section. It's almost done. Almost done. We almost get everything done. This is already the 5th lecture. So the next one will be pretty much like, okay, it's toward the completion of the thermodynamics module. All right, so let me pull up the next handout. All right, any questions up to this point? All right, so far so good. All right, so I'm just gonna talk about stuff a little bit, and that's it for today. Just give you like an overview or like a teaser of what is supposed to happen. All right, let me pull up that slide. Oh, I don't have it here. Wait a second. Oh. Oh, whoa. All right, so maybe I forgot to download. Okay, give me a second, guys. Maybe just okay, 1 second. Okay. All right, let me grab it from the drive first. Give me 1 second here. All right. Sorry, I thought I had it here. All right, but anyway, during the meantime, you guys pull up the handout number 3 as well. Did I post it yet? I think I posted, yeah. Shoot. It would be bad. Like, Ajahn, I haven't seen that third handout either. That would be bad. Oh no. Did I forget? You guys got, oh yes, mean you got that number 3. Okay, thank you. Oh shoot, it will be bad. I forgot. Okay, here we go. All right. Okay, let me share the screen one more time. All right. Okay. There you go. So yeah, there are more to thermodynamics. Well, it's not more, it's more like it's the application. Okay, so what we are going to do next time, and I think it's going to be realistic in terms of how to utilize the theory that we have been built upon, is to explain heat engines, guys. That's for the whole thing. I mean, I think maybe this is the highlight of this segments right here, is at least you can, you know, make connections to the realistic stuff, which is the engine. The idea is very simple, right? We as a human, of course, trying to as we're trying to steal or try to make use of the energy around us. And once we experience that the hot stuff is doing something, yeah, when we put them in thermal contact with the cold stuff, we know that heat is flowing, right? Heat flow from hot to cold. So human trying to get something to put in between and wishful, well, I hope they wish. Now it's impossible. Okay, so they're with the wishful thinking of try to redirect portion of that energy to perform something useful. Does that make sense to you? All right, because we say, hey, something hot is like high energy. And then when you put something colder in thermal contact, you guys know something is flowing that we named heat. Then we try to come up with the idea that, hey, if we can put some engine in between and we can redirect portion of that flow and use that to perform some useful for us, then we should be able to, all right, find hot stuff and then, attach something in between and then steal some energy from the nature. That's the whole idea. Okay. However, the nature is tricky. They do not allow us to do things like that easily. That's the key. But anyway, everything is still based on law of nature, which is the conservation of energy. So that means if you can pull the energy down from whatever the hot stuff that you are trying to get to, okay, let me do color coded here. So if you can draw some heat from the cold stuff, and eventually you dump some heat away in the cold region of your system, and then of course you're going to figure out like, hey, I want something from those transfer, but because of the conservation of energy, that amount of heat that is difference between the incoming and outgoing must be exactly the same as the work that the engine can perform. Does it sound easy enough? Yeah, it's conservation of energy. So the amount of work that the engine can do is just different from the amount. I put the absolute sign into it, so we don't have to worry about the sign of the heat at this point. So the energy that flow in, subtract the energy that you have to discard or have to trash out. The difference is just the amount of work that you collect and do something useful to it. All right, so there is a word that your friend just throw in, the perpetual machine, right? So it would be nice if you don't need to throw anything away at all. If you don't have to throw anything away, that means you can redirect the energy in your whatever environments and stuff, and then you redirect the whole energy into something useful right away. That's also possible. I mean, no, not possible. I'm saying that's whatever in your head that you want. I mean, in theory, you think that you want to do that. It turns out that is not allowed. This universe does not allow you to do that. And that comes the efficiency of the engine. So when you talk about the efficiency, if you can do this, you can redirect all of the energy from the nature into something useful that is 100% efficient engine. But it turns out, no, it's not. What you are getting with respect to what you are receiving is giving you the ratio that something is sort of as useful. So my way of remembering, or well, that's the way of efficiency is being defined, is what you get over what you have, or what you are given, or what you get, what you have to provide. For example, like you are studying right now, I'm providing you with the thermodynamics material, how much you understand. So that would be the efficiency of learning this lecture right here, right? So that's a concept of efficiency is easy. Oops, sorry. Efficiency is what you get over what is provided to you. Okay, but of course, you already saw that the amount of what you get, it depends on the difference between the provided and the one that you cannot do anything with it. You have to throw them away. So it's a Q hot over Q cold. Q hot is the one that you steal from the hot stuff, and the Q cold is the one that you have to throw out. And then you can readjust your formula a little bit. So you can say the efficiency depends on how much you have to trash out. Cannot keep it to yourself, divided by the amount of heat that actually flow into the engine. Does that make sense? All right, so this is just the main diagram that we can use. The hot stuff that provide a lot of energy, you can name it a hot reservoir. So it's like a reservoir of energy at high temperature, right? When we say high temperature means high energy. So when you have a big reservoir of that, so that means that is your source of the energy. And down here is, you can name it like a cold reservoir. Like, for example, you can say the temperature outside that cold, or that could be hot reservoir. It depends on what kind of engine you're trying to connect to. But that's another kind of reservoir that adds lower temperature. Sounds good? All right. So I hope by looking at this diagram, you start to see that, oh, Ajahn, I can understand what does it mean by efficiency. All right. We can look at the example to do the real calculation later, but not today. My point is this. Here we go. So what you are having right now is depends on how you would like to run your engine as well. But Ajahn, why don't we run it backward? Is it possible that I can run the engine backward by giving some heat to the hot reservoir and pull some energy from the cold reservoir? Is it possible? But yeah, but if you want to do this, you have to reverse the direction of the work as well. And this is the same diagram, but everything runs backwards. And can you imagine what this is? Yeah, this is air conditioner. I am in this room, cooler than outside. The air conditioner is trying to pull some energy from the colder part, which is in this room right here, maybe 25 degrees Celsius, and dump the energy outside, which is higher in temperature. So this actually is air conditioner. Make sense? But because this device or this engine right here try to do something opposite to the nature flow, so we name it the heat pump. It's just like a water pump. The water try to flow from high to low. When you want to bring the water from low to high, you use a water pump. Same thing over here. The heat try to flow from hot to cold, but when you want to bring the heat from cold to hot, you bring in the heat pump. Make sense? But no matter what you're trying to do, conservation of energy has to stay with us. So the amount of heat that you dump out must be the same as the heat that you extract from the cold portion plus the work that you put into the pump. So you cannot get away from it. Q hot must be equal to the work plus Q cold. All right, so this is the whole thing that we are trying to get to is, okay, if this is the case, Ajahn does not allow 100% efficient engine to run. Next time, we will answer what is the best engine in the universe. Even Thanos cannot build a better one as long as they're using the same physics. Wow. Tony Stark cannot build any machine that runs better than this one. All right, as long as they're trying to use thermal engine, of course. All right, other technologies excluded. And we will answer the question, why can't we use your body temperature to charge your iPhone or whatever Android machine? That's why it's not possible, or why we don't have that kind of machine to do that just yet. Okay, so that will be the next time that we going to look at the application of the first law of thermodynamics. Sounds like a good plan, guys? Okay, all right. So if this is good, that is it for today's lecture. See you guys next week. Okay.